Solar panels are most efficient at a 90-degree angle to the sun's rays. A tracking system can reposition solar panels throughout the day to maintain the optimal 90-degree angle. However, these systems consume energy in the process. The power consumption must be minimized in order to realize the benefit. This project compares several methods of solar tracking control to a traditional stationary position. Both power generated and power consumed are recorded as a means of quantifying the comparison. The generated power is stored in a battery, and the control system is powered from the battery. This makes the system self-sustaining. The following is a description of the different control modes. In GPS mode, the first step is to collect the NEMIA standard data from satellites. Next, the data is parsed to obtain latitude, longitude, and time. This is used to calculate the zenith and azimuth angles of the sun. The motors are then activated to adjust the panel to align with the calculated angles. The linear actuators are not equipped with encoders, which makes it difficult for the controller to know their current position. Potentiometers on a 3D printed mount are used to determine the angle of the panel on both axes. The linear actuators are in Cartesian angles, so the spherical angles of the sun must be converted to Cartesian to make a comparison. Next, the motors move in the appropriate direction and the position is reevaluated. This process repeats until the desired position is within a certain threshold. This is a demonstration of LDR mode and how it aligns to the light source. In LDR mode, the 3D printed mount has walls that will cast shadows on some of the LDRs, causing them to have a lower resistance. The TI Launchpad reads the values of each LDR and compares them in an algorithm. The motors are then adjusted accordingly to align the panel until all 4 LDRs have equal values. In LDR mode, in the comparison algorithm, the controller first determines which sensor receives the most amount of light. The brightest sensor is compared with its north-south adjacent sensor. Then, the associated north-south motor is moved in the direction that allows the sensors to receive equal amounts of light. In the next step, the original brightest sensor is compared with its east-west adjacent sensor. The associated east-west motor is moved in the direction that allows the sensors to receive equal amounts of light. In hybrid mode, both LDR mode and GPS mode are utilized. If LDR values drop below a certain threshold, this indicates insufficient lighting conditions for successful use of LDR mode. Instead, the controller will use GPS mode until lighting conditions improve. Power monitoring is implemented for comparison of modes. The power monitoring system is fully automated and stores data every minute throughout the experiment. Power monitoring is conducted by a secondary system from the main tracking system. This ensures that observation methods of the experiment do not affect the data. This graph shows the output power generated by each mode tested. Due to inclement weather, no data was collected for hybrid mode. And due to technical difficulties, some data was lost and there is a gap in the GPS data. Sharp drops in the data were caused by clouds passing over the sun. This was determined by reviewing pictures taken during the corresponding time intervals. There is a downward trend in the late afternoon for all 3 plots. This is because the panel was at a limited range of motion and was at its maximum angle. Even with the sun out of range, the control mode still performed better than the stationary because the panel was still more optimally positioned. This graph shows the input power consumed by the system for both control modes. There are spikes in both plots that occur every 20 minutes. This is when the controller exits low power mode and the motors are powered to move the panel. LDR mode appears to perform better in terms of power generated, but GPS mode appears to perform better in terms of power consumed. To determine which mode is best, net efficiency must be considered, which is shown in Graph 3. Overall, LDR mode has the highest efficiency throughout the day. There is not enough data to compare GPS mode to stationary when the sun is in the panel's range. Because LDR mode generated more power than GPS mode, it appears to track the sun more accurately, explaining why it performed better overall.